Today we're going to talk about the product rule of derivatives. Now, let me just warn you straight off. Today's topic is going to be used in terms of just what we might call a technique, because every derivative that we're going to calculate today, and today only, can be found using yesterday's notation. So remember, yesterday we had a short form of finding derivatives where terms were written in the form cx to the n, and we said the derivative was equal to cn x to the n minus 1. Today we'll be able to write every single term as a sum or difference of this form. So in essence, we won't have to use this product rule today, but we need the technique because as you go further and further into these calculations, you're going to end up with terms that can't be written in this form, and it will be necessary to use the product rule when we have products of more than one function. So if I wanted to find the derivative, like I said, of this form, all I'd have to do is FOIL this out. I could get 8x squared, there's 2 and 20, which makes 22x, plus 5, that's h of x. And I could say, well, the derivative of that, because each term in this can be written as cx to the n form, get 16x plus 22 and be done. But once again, we're going to use a different technique to find this. Let's talk about what the product rule means. And you'd think, since I have the product of two different functions here, it's going to play in this new process. Product rule states that if I have a function that's made up of a product of two functions, the derivative of that function, f times g, is given by the following. You take the derivative of the first function, multiply it by the second function, add that to the first function multiplied by the derivative of the second. So let's apply it to the last problem we did. In this case, I have two functions, f and g, that make up the h function. My derivative of my f function is equal to 2. My derivative of my g function is equal to 4. Now the product rule states, once again, I take f g prime plus g f prime, and I get h prime. So let's go ahead and do that. And I'll come over here. F is 2x plus 5. I'm going to multiply that by g prime, which is 4. To that, I'll add the g function, which is 4x plus 1, multiplied by the derivative of the f function, 2. Distribute through, I get 8x plus 20 plus 8x plus 2, which I end up with 16x plus 22. And if we look back at our other calculation, 16x plus 22, we get the same value. Granted, this seems like it might take a little bit longer, it's a little more complicated, but once again, we're using the techniques today because they're going to eventually help us in the long run. So let's take a look at this function. Here is once again my f, and then my g. Therefore, f prime is equal to 10x to the 9th, and g prime is equal to 2x plus 8. Find my derivative, h prime. I take the f function, multiply it by the derivative of the g function, then add that to the g function, plus the derivative of the f function. Now, once you get to calculus, you'll be asked to simplify these. I could distribute all this in and then add like terms, but I see right off the bat that I'm going to have some GCF going on. I can factor out an x to the 9th. Once I factor that out, I'm left with an x times 2x plus 8 plus 10 times x squared plus 8x plus 7. Cleaning that up, I have x to the 9th times 2x squared plus 8x plus 10x squared plus 80x plus 70. So that's x to the 9th, 12x squared plus 88x plus 70. And that's my derivative. Let's take a look at another problem. Now, the issue with this is that it's not written in cx to the n form. So I don't know how to find the derivative of these terms. I need to change this. So I have h of x equals x to the negative 2 times 4 plus 3x to the negative 3. Therefore, if I call this my f function and this my g function, I can take each derivative now. F prime is equal to negative 2x to the negative 3, whereas g prime is equal to negative 9x to the negative 4. Once again, we'll find h prime by going f g prime plus g f prime. So I have x to the negative 2 multiplied by negative 9x to the negative 4 plus 4 plus 3x to the negative 3 multiplied by negative 2x to the negative 3. Once again, I have some common terms, and I might even be able to take and add some like terms. This doesn't appear to be too big, so let's just multiply it out now that I'm thinking of it. We have negative 9x to the negative 6 minus 8x to the negative 3 plus negative 6x to the negative 6. I can add some like terms, so the derivative is negative 15x to the negative 6 minus 8x to the negative 3. If I wanted to clean that up a little bit, negative 15 over x to the 6 minus 8 over x cubed. And that's my derivative. Lastly, we're going to find the derivative of the function h of x at a specific point. So now we're actually looking for a numerical value for the derivative. Once again, f and g. Find h prime. I'm going to need f prime, which I know is 3x squared. Turns out g prime has the same value of 3x squared. So I'm going to once again take fg prime plus gf prime. F is x cubed minus 1. G prime is 3x squared. G is x cubed plus 1. F prime is 3x squared. And what I want to do is I want to find my derivative value when x equals 1. So rather than clean all this up, I'm just going to plug a 1 in. I'm going to find h prime at 1. So in this case, I have 3 times 1 squared minus 1 times 1 plus 3 times 1 squared times 1 plus 1. First term goes completely. Second term gives me 3 times 2, or 6. So that's the actual slope of the tangent at the point 1, 0. I could write the equation on the line if I wanted to, but the problem doesn't ask me to. So hopefully that technique helped us out a little bit. Didn't have to do some foiling. Fill out your summary, and we'll get back to you tomorrow.